Hello, it's Keith here, and this is lesson 23 of the simple series of my 650 assembly programming tutorials. Today we're looking at a sprite clipping routine. This is a routine that allows the sprites to go partially off the screen, and today's example will work on the Atari 800 and 5200. You can see we've got the two here, and if I can remember the controls, here we go. You can see my Chibico character is able to move around the screen, and the sprite is able to go partially off the screen with some clipping there. That's the 5200 version, I think that is there. This is the 800 version. Different set of keys, but the function works again. You can see the Chibico character is able to go off the screen at various points, and basically, of course, these two are essentially the same code. The joystick reading routine is slightly different, and some of the graphics ports maybe are different, but basically it's the same code. That's why it works on two systems. Now, what we're looking at today is the code that is doing the clipping. It's some logic code that recalculates the maths, and it's an upgraded version of the sprite routine. In the simple series in the past, we've looked at joystick reading and we've looked at basic bitmap routines and how to set up a screen. We're not going to cover those bits today. I'm assuming you know them, or you don't care, or you can figure it out yourself. So please go to the website, download today's example, have a go with it. And if you still don't understand how those factors work, the joystick reading, the screen setup, how they work, please see the other simple series examples where that's been covered. Now, the screen we're working on today is a 4-color screen, and it's effectively 160 by 192 area we're working on. But for our games, I'm always working within 8-bit coordinates, and we need the coordinate system to allow for sprite to be partially off screen. And so to do this, I use a logical coordinate system, which I then convert to the physical pixels on the screen. So let's go over to my theatre screen and let's have a look at that logical screen space. So here we go. So this is the logical coordinates I use. Basically, typically speaking, I treat the screen as being based around a 256 by 192 pixel visible screen. That's the screen that systems like the MSX and the Spectrum support. Some systems have a larger screen like the Amstrad CPC, which is by default 320 by 200, but I actually on that system shrink it down to a 256 by 192 screen. For compatibility, it's easier to get everything working in the same format. And so that's what we're going to be doing again today. Now, the way my coordinate systems work is we've got a visible screen, which is represented by this white area in the middle here. And we've got an invisible area of the screen, which is this dark area here. Now, the coordinates of the entire logical screen are from 00 to 255, 255, because we're working in 8-bit coordinates, because that's the fastest way to work on an 8-bit system. But within those coordinates, only a small middle area of the screen is visible, from here all the way down to here. And this area is 128 by 96 in size, and this is a nice easy way to work because my target screen size is 256 by 192, and so this means that a logical unit is 2 pixels. So if you think of my Chibico bitmap, which we use in all of my tutorials, which is 48 by 48 in pixels, in logical units that's 24 by 24, and we'll pass the coordinates for the drawing and the coordinates for the size to my cropping routine, which will convert them into pixels for us to draw later on. Now, if you imagine the Chibico here is at this logical position here, and it's partially off the screen. So only this corner here is in the visible area, so that's the only part that will be shown. And that's what the cropping routine does. It calculates the part that needs to be shown, and then we've got an upgraded drawing routine, which will actually deal with the task of drawing it. Okay, let's go over to our code and let's see that. So here's the code for today's example. It's this A52 bitmap clipping. This is the file that we're using today. And the first thing we're doing here is we're defining our logical screen. Now on this system, our logical screen is 160 units by 96. Now, in this case, our image is actually half the width. By default, it would be 48 by 48 in pixels. But on this system, the pixels are actually double width. So the screen in logical units is actually 160. So it's kind of irregular, this system, because, as I say, the pixels are double width, so they're more chunky. And to maintain the functionality across all of the systems, we're halving the width of the sprite and keeping the logical units the same. Now, we've got a variety of variables we're setting up here. We've got some temporary variables in the 0 page we're using here. These mimic the Z80 registers, but their actual meaning has no symbolism relating to the letters, except for the fact that BC are a pair that make up a 16-bit pairs BC, and HL and IXL and IXH combine to make IX, and the same with IY. And we'll see these in use during our code for drawing the sprite to the screen. As I say, they're just temporary variables, so to speak. Sprite H clip is more important though. This is something that's used after the drawing of each line of our sprite before the next line. Now we're going to need to discuss the theory of how we're actually going to crop our sprite when we draw it to the screen. Okay, so we've got our visible screen, and if you imagine that this is our visible screen, and if you can imagine, I can actually draw a rectangle without it looking like a wibbly mess, and then we've got a sprite somewhere on that screen. Maybe that's our sprite. Now our sprite, whatever its shape, is of course actually going to be within some kind of square or rectangle as far as us plotting it onto the screen, and we're going to move our sprite around the screen. Now if our sprite is all on the screen, then we don't need to do really anything more complex than we did last time in the simple series. The problem is when our sprite goes off the screen, we're going to have to do things, and what we're going to have to do is going to be very different depending on where that sprite is. For example, if our sprite goes off the top of the screen, well, we're going to have to skip some of the sprites of the source data, and then we're going to have to move the starting position to here, and we're going to have to change the height of the sprite to this remaining part here. That's if it goes off the top of the screen, but if it goes off the bottom of the screen, the procedure is going to be different. We're going to need to change the height, but we're not going to need to change the starting position because we're starting from the beginning of the sprite. We're just going to skip the bottom part. However, if it goes over the left-hand side of the screen, well, the procedure is going to be quite different. We're going to have to change the width, we're going to have to change the starting position, and we're going to have to skip some of the bytes before the first line, but then also after the first line we're going to have to skip the bytes of each consecutive line to draw the part that actually appears on the screen. Now that's on the left hand side. The right hand side is different again. We once again need to change the width, but this time we don't skip anything from the start of the sprite, but again after each line we need to skip part of the sprite before the next line. And that's the cases where it's over one side. Well, what happens if it's over two in the corners? And fun fact, Chibi Akamas couldn't do that right. There was a bug in the code because basically I was really struggling to write this code. You know, I'm not very good at maths and things, so I really barely managed to make a code that could do the clipping properly in Chibi Akamas, and it didn't work properly in the corners. And it didn't really matter on that game. It hardly ever happened, but it didn't work. This one does work. I've actually got better at programming miraculously, so we'll be looking at this better version today. Okay, so we've got our joystick routines here. Our drawing routines here are the first thing we're going to look at that are the things that's changed. So when we want to draw our player to the screen, we've got the BC registers loaded with the current position of our player. We then load the IY pair with the memory address of the source bitmap data. We load H with the width of our sprite in logical units, so 24 logical units, and L with the height, 24 logical units, that's 48 lines. And then we run a routine called doCrop, which we'll have a look at in just a moment. Now doCrop will convert the width and the position according to the cropping that's required, and also converting to physical pixel units. So that's going to do that job for us, but it's going to do something else. If the sprite's completely off the screen, it's going to set the carry, and that's to tell us give up, there's nothing to draw. So in that case we would just return here, otherwise we'll do the sprite drawing. Now we'll look at that sprite drawing routine in just a moment. First of all, we're going to discuss the cropping procedure. Now the cropping procedure starts here, and basically the first thing we do is we load the Y register with 0, and Y is 0 throughout this code, and we load D and E, which are some temporary registers that we use, or 0 page entries rather. These are going to be used for our calculations of the cropping. We also zero the sprite H clip, and the sprite H clip is what I described to you a moment ago. It's where the sprite is partially on the screen, and after each line we need to skip part of the sprite. So that's what that does, and we're going to see that later on. We'll initialize it and then we'll see it in our sprite drawing code. Okay, so we're going to crop the top of the sprite. So we're loading the Y position that the sprite's going to be drawn, and we're going to then subtract the first line of the visible screen in logical units. So basically by doing this, if our starting position is below the first line, this is going to go negative. If it doesn't go negative, then there's nothing to crop. So basically we're below the minimum visible units of the screen, and we don't need to crop any of the top of the sprite. If we do need to crop part of the top of the sprite, we convert our negative number into a positive one, and this is now the amount of pixels we need to remove from the top of the sprite as part of our crop. We then compare this to the height of the sprite, because if it's the entire height of the sprite, then there's nothing left on the screen and we want to give up. To give up, we just set the carry and return, and the routine that called this will then give up on drawing the sprite. Now, if the height that we need to remove isn't the entire sprite, then we store this for later in ZE, and we then set the Y position to 0. We then store this in C, and C has now been converted by subtracting the minimum visible logical unit. So this isn't still in logical units, but it's now 0 based on the first visible pixel. So that's closer to what we need to draw, and we'll convert it to a pixel unit, a line number later on. Okay, so we've cropped the top of the sprite. We're now going to do the same for the bottom. So we now add the height of the sprite to the starting position, and we compare this to the height of the screen in logical units. Now, if this is over the height of the screen in logical units, then the sprite is partially off the screen on the bottom. So we now see if the amount we need to remove from the bottom is the height of the sprite, and if it is, again, we give up, but if it's not, this is now the amount we need to remove from the bottom. So ZE is the amount to remove from the top, and ZD is the amount to remove from the bottom. Okay, so what we do now is we add these two together, and we see if anything needs to be removed from the top or the bottom of the sprite, and if they don't, we just stop. If they do, then we convert this to an amount to remove from the height, and we update the new height of the sprite. So this is calculating the new height, whether we've cropped the top or the bottom. Okay, but now what we need to do is we need to deal with the case where the sprite is partially off the top of the screen. Because if you remember, if the sprite's off the top of the screen, we're going to need to remove this part here. We're going to need to remove part of the source bitmap data of our sprite before we try and draw anything. And we're going to do that right now. So what we're doing here is we're loading the number of logical units to remove from the top of the sprite, sending that to X, which is going to be our counter, and then we calculate the number of bytes in each logical unit of height based on the number of bytes in the width of our sprite here. So we're converting this to a number of bytes to remove for each logical line. Then what we're doing is we're taking our source bitmap data in the 0 page pairs ZIY, ZIYH and ZIYL, and we're repeatedly adding the width of the sprite in bytes to remove a line, and we're just doing that repeatedly until X reaches 0. Now, of course, this isn't the most efficient way speed-wise of multiplying, but this only happens once per time that the sprite is drawn, and only when the sprite is partially off the screen. So this is a fairly rare case, and so I didn't really think it was worth using any kind of lookup table or pre-calculated value to try and speed it up. Just to say it's a very rare case this happens. Okay, so that's now calculated our new height and our new starting position. So we've now done the vertical cropping of the sprite. So we're now going to do the horizontal cropping, and we do basically the same thing. So we reset our D and our E because we don't need the old values anymore. And now we take our starting X position, we subtract the minimum X visible logical unit, and we see if that is completely on the screen, and if it is, then we just skip the next part. But if it's partially off screen, again we compare and see if the amount that we need to remove is the entire width of the sprite, and if it is, we give up. If it's not, we store the amount we want to remove, and we set the X position to 0. So this is a starting X position because our sprite is at the far left of the screen, somewhere like that. So we're going to crop that accordingly. Okay, so that's what we're doing there, and then we're going to do the same for the right hand side. So we're storing our new X position, and then we're adding the width and comparing to the visible width of the logical screen. And again, if we're partially off the screen on the right hand side now, we're going to see if the amount we need to remove from the right hand side is the entire width of the sprite. If it's not, we store the amount to remove from the right in ZD. Of course, ZE is the amount to remove from the left side, and we can add these two together, and then we just need to convert this to a number of bytes for our sprite because we're working in logical units, but we need to calculate this into bytes. And this is the amount we need to remove after each line of our sprite, because whether our sprite is on the far right or on the far left, we need to remove part of the source bitmap data after each line of the sprite, and that's what we're calculating here. So we're adding the two together, converting them to a byte count, and then we're storing that in sprite hclip, which we'll skip after each drawn line of the sprite. But what we need to do next is we need to calculate the new width of our sprite. So what we're doing here is we are converting the calculated logical unit into a byte count. We are then updating the new width in bytes here, and then we're going to take the amount removed from the left in ZE, convert that to a number of bytes, and add that to our source bitmap data, because of course if we've got our sprite on the screen, well, if it's on the right hand side we start from the first pixel of our sprite, but if it's on the left hand side we need to skip some of the bytes before we even start drawing, and that is what we're calculating here, and we're adding that to our source bitmap data in the IY pair, and that's going to be our bitmap data. Now we've now calculated all of our crops, and the last thing we need to do is convert our logical units into a physical number of units. So we're converting our xpos and our width into a number of bytes, and we're doing that by effectively dividing by 4, and we're converting our lines from a number of logical units into a number of pixel lines by effectively multiplying by 2. And this has now converted the BC XY pair into a number of bytes and a number of lines, and the HL width height pair into a number of bytes and a number of lines. We then clear our carry to tell the calling routine that there's something to draw, and we return. Okay, so now we're going to draw our sprite to the screen. So this actually returns us back here, and we start the drawing routine here. What we do is we convert our XY position into a memory address, and this is returned in DE, and then we're going to jump down to here, and this is the routine that draws the first line. The part that was before this is for the consecutive lines, and we'll see that in just a moment. So we're loading Y with 0. Y is going to be our bitmap offset for our reading and writing, and then what we're doing here is we're loading X with the width that we want to do, and then we are transferring bytes from the source in IY, the source bitmap of the Chibico. We're XORing them, EORing them with the screen data, and we are storing that back to the screen using Y as an offset each time. We then increment Y, decrement X, and repeat until X reaches 0, which is the width of our sprite. Now, once we've done that, we then decrease our line count, and if we've got more lines to draw, we jump back up to here. Now this is the next line routine, and this is going to recalculate the destination memory address for the next line of our screen memory, and all we need to do for that is add hexadecimal 28, which is 40 bytes per line, and this moves us down one line. We increment the high part of the DE pair if needed, and that has calculated our destination memory address, but we still need to update our source bitmap data. Now we used Y as an offset, so we basically transfer Y to the accumulator. We add the current memory address of the bitmap data in the IY pair, and we update the high part of that if needed, and that has moved us along by the number of bytes that we drew to the screen. But remember, if our sprite is off the side of the screen on the right or the left, we will need to skip some bytes before we draw the next line, and that's what we're going to do here. So we load in that sprite hclip value that we calculated earlier, and if it's not 0, we add it to the memory address of the sprite, and that will move us along to the next pixel that we want to draw to the screen, and then we simply repeat our drawing routine until our sprite is done and it's been drawn to the screen. So there we go. So that's the example that you saw today. Now, one thing I would point out, the sprite drawing example, I don't know if you noticed, is rather flickery. You can see it here. It's flickering something crazy. It's actually being improved by my the slow frame rate of my Zoom, but it's flickering, and the reason for that is we're updating it whether it's moved or not. Now, if you were writing a real piece of code, a practical example, you wouldn't want to do that, obviously, but this is a simple test, and so it doesn't matter for a simple example like this. But if you are looking to write a proper game, you would definitely want to do that. Now, the other thing you would probably want to do is you would want to maybe have multiple sprite routines, because if your sprite is entirely on the screen, then doing all of these extra calculations with regards to the new line commands and things is possibly going to be a little bit wasteful, and you might want to have a more efficient routine to draw the sprites directly to the screen. That's how Chibi Akuma's worked. There were multiple sprite routines. There were fast ones, there were slow ones, there were ones for transparency. So that might be something to consider as well. But as I say, this is really just there as an example to show you how you can crop a sprite. I'm not saying it's the best routine, but as always, you're welcome to use it if you find it beneficial, and if you can think of a better way to improve it, you're welcome to make a better one and make your own YouTube video explaining how you did it better. You're welcome to do that as well. Have some fun with it and make whatever you can of it. Anyway, hope you've enjoyed this today. Thanks for watching, and goodbye.